And I'll just introduce you for a few seconds and then you can get started.
Sounds good.
So, welcome everyone to UR's Master's Thesis Defense. Welcome to the committee, Sergey and Stefan, and also the students that are able to attend, Ben and Prashant. So we are all in different locations, in different continents. I hope the Zoom works fine. I had a little problem with the connection a few seconds ago. And should there be any problem, and I'm kind of in and out momentarily for a few minutes or a few seconds, whatever, please don't, please just continue with your presentation. Don't worry about me. Anyway, I'm very pleased to introduce Ur to all of you. And Ur has been he worked with me as an undergraduate, and then he stayed over for the master's degree at Dartmouth because he liked the work he was doing. And I'm pleased that we are continually able to probe deeper and deeper into the sort of things that he has been working on, which is to produce machine verified proofs that you will hear a lot from him today. And with that, Ur, please get started.
Thank you very much for the introduction, Professor. Hi, everyone. Thank you all for coming to my presentation. Today, I will be defending my master's thesis titled A Machine Verified Proof of Linearizability for a Q Algorithm. Professor Prasad Jayanti has advised me throughout my work on this project, and Professor Sergey Bratus and Professor Stefan Mertz of INRAE Nancy in France have both generously agreed to serve on my thesis examination committee. I'd like to thank them all for their interest in my research, and I am looking forward to their feedback. I would like to start by describing what has been achieved within this thesis project in very broad strokes. So linearizability is a very desirable property of concurrent algorithms. Keep in mind that we'll define all this later on, but this is the general idea. So linearizability is a very desirable property of concurrent algorithms whose correctness is often difficult to prove. And even when proven, these proofs are challenging to comprehend and verify. So a reader reading the description of such an algorithm and trying to understand it, then understand its proof, and trying to assure themselves that the algorithm is indeed linearizable, might have a difficult time. This is why it is quite desirable to have machine verified proofs of linearizability. Assume we have a proof of linearizability for some algorithm, and we know this proof to be certified by a machine. That is to say, for instance, with the help of a proof assistance software, which can take formal proofs provided in a certain format and certify whether these proofs are indeed correct or not. If we can provide a formal proof of linearizability and have it be verified by such a program, then the human reader does not have to do anything to verify the claimed linearizability, saving them a lot of effort. Then how do we go about producing such machine verified proofs of linearizability? Linearizability happens to be a quite abstract concept. Therefore, it is challenging to prove an algorithm to be linearizable simply based off the definition of linearizability. And as part of our work, we came up with a technique that allows us to circumvent this challenge by reducing this task to simply proving an invariant, a logical assertion about a slightly different yet closely related algorithm for any algorithm that we want to prove linearizable. It turns out that proof assistants are quite apt at handling this type of proofs, proving invariants of algorithms correct. Therefore, this reduction allows us to produce machine verified proofs of linearizability. And for our project, we use the TLA proof system based on the specification language TLA+, and we'll elaborate on our choice of tool later on in the presentation, but I should note that the TLA+ proof system is developed by a number of researchers in France and INRAE Nancy in collaboration with Microsoft Research, and Professor Stefan Mertz is among the leading researchers leading this effort. So I am very lucky to have him on my committee and have his feedback on my project. In fact, the technique I just described was something we first developed last year as I was working on my undergraduate honors thesis. And when I presented this work last year, the technique we had came up with had only been applied to relatively simple algorithms. We had conjectured that this was a generalizable technique, most likely applicable to any linearizable algorithm. And though we had a promising result for a simplified snapshot algorithm, we hadn't been able to apply it to a significant algorithm at that time. So for my master's thesis, I sought to prove the Herlihy-Wing Q algorithm linearizable. This algorithm is a well-known algorithm first provided in the same paper which defines the concept of linearizability, and is an algorithm whose proof of linearizability is known to be intricate and challenging. It occupies a third of the paper and requires a sizable appendix for Herlihy-Wing to go through the entire proof. And not even that, for the most part, a sketch. So therefore, we thought that if we can prove this algorithm to be linearizable within our framework, this would give us great confidence that our technique is indeed generalizable to any linearizable algorithm. And this is exactly what I was able to achieve. We were able to prove the Herlihy-Wing algorithm linearizable using our technique. So this was a high-level description of what I have done for my thesis. Having provided the context, I will now elaborate on each of the components that I have described throughout my presentation today. And here's how I structured this presentation. I will start by providing the framework for the problem we are studying. I will establish the computational model we're working with, within which I will then define the property of linearizability for an algorithm. So the model of computation we are concerned with is a concurrent computing system. A concurrent system comprises a collection of independent processes that compute concurrently, that is, simultaneously. And these computations are in the shape of a program. So each process has a program that it executes. In addition, each process also has access to certain parts of memory of the system. A program consists of a sequence of instructions, which we can think of as a sequence of lines of code. And each instruction of the program, so each line of the code of the program, describes how the process executing the program interacts with the memory by accessing and modifying variables that are stored in the memory. We note that the relative speed at which processes execute these instructions in their program might vary arbitrarily. There might be a process that executes successive lines very quickly one after the other, and there might be another process that takes a lot of time in transitioning from one instruction to the other. And this is the definition for asynchrony. When the execution speed of processes change arbitrarily over time, we refer to the processes as being asynchronous, which is the case in most concurrent systems. In each line, so in each instruction, a process can read from and modify its local memory, where its local variables are stored. And these variables are memory words, so they are pieces of data of a fixed size that are stored in memory. And local variables, they are only available to the specific process to which the local memory is assigned to. In addition to this, processes also have access to shared memory, which can be accessed by any number of processes. And this allows for communication between processes, which is of essential importance when coming up with algorithms that operate in concurrent systems. The building blocks of this communication enabled by shared memory are what we call atomic shared objects. These are abstractions of the memory on which processes can apply operations that change the internal state of these objects and receive responses to the operations they have invoked. And a shared object is atomic if whenever a process invokes an operation on the object, the change in state, the determining of the response, and the returning of these responses to the invoking processes, they all happen instantaneously. It shouldn't come off as surprising then that this is a highly desirable property, because as processes operate concurrently and are asynchronous, it is very easy for a process to get into the way of another process invoking an operation on a non-atomic object. For instance, a process could modify certain variables that another process relies on during its execution of a certain operation on the object, and this might cause unexpected or even incorrect behavior in how the operation takes effect. But the same problem does no longer exist for an atomic object, because each such operation takes effect instantaneously, leaving zero room for errors of this type. So we have understood that the availability of atomic objects help communication between processes considerably. But one might ask the question, what kinds of atomic objects are available in practice? The answer to this question depends on the hardware that is being used, but most hardware have a limited selection of shared atomic objects available for use by default. And popular examples of this include read-write objects, which a process can read from and write into, the fetch and store objects, whose stored value can be retrieved and changed with something new in a single operation, and fetch and increment objects, whose stored value is incremented by a certain amount as they are retrieved. Of course, these objects are quite often not sufficient for the programs that would like to design for concurrent systems. Frequently, there is a need for types of atomic objects that are not supported by the hardware to system by default, and that embody useful abstract data structures, maybe hash tables, stacks, and queues that we are familiar with. So what do we do here? How do we bridge this gap between what we need and what is available to us? The answer to this should be obvious from the question. We should simply be using whatever is available to us. And this would be done by describing in software algorithms that implement the atomic objects of the desired types using atomic objects that are already available. Well, what does it mean to implement some object using atomic objects? Well, an algorithm implements an object and it provides a method for each of the supported operations of the object. For instance, here we have a diagram of the implementation of a queue object. This implementation must provide methods in code for the enqueuing and dequeuing operations. And any process can invoke any of these two methods on the object and they get a response in return. Enqueuing should simply return an acknowledgement that the operation has taken effect, and dequeuing should remove the earliest enqueued element among the ones in the queue. And as these methods get executed, the instructions in the method may apply operations on the atomic objects that are already available in the system. Here, covered in red, this could be an array, this could be any fundamental structure that we use to model this structure. And yeah, as I mentioned, these would be the base objects for the implementation. And we note that when a process calls and executes one of the methods, the execution of the method lasts over a duration. And this depends on, this duration length depends on the length of the code for the method and the speed at which the process executes code. Then if these methods are potentially not instantaneous, they should make us ask the question, what is the correctness criterion for an implementation? Because these are definitely not atomic by default. Well, here's a small thought experiment. In this diagram, on the vertical axis, we have two processes, and the horizontal axis denotes time. Each line segment we have here corresponds to a method that is executed by the process, which it's vertically aligned with. And for each method, the left endpoint is the point in time which the method is invoked, and the right endpoint is the point in time which the method returns a response. And in this diagram, we have two processes invoking the methods of an algorithm that implements a queue object named Q. Here, P1 invokes Q and Q5 and returns. P2 invokes Q and Q10 and returns. Then P1 invokes QDQ and returns P2, and then finally P2 invokes QDQ and returns. So the enqueues, we know that they return acknowledgements. So there's nothing interesting here. In fact, let's denote what they return. So this returns an ACK, and this returns an acknowledgement. So what should the dequeues return? What should this first one return?
Five.
Yeah, because 5 was the thing that was enqueued first. The enqueuing of 5 took effect throughout this line segment. It's been done before the time was ever enqueued. So the first dequeue should return a 5, and then the second one that would return a 10. This was a fairly straightforward example because there are no overlaps between any of the methods. So it is very clear what each operation should be doing. Here is a slightly more interesting example, even though the change is very minor. It is now simply the case that P2 began its enqueuing of 10 before P1's enqueuing of 5 returned. Every other operation remains the same. And before thinking about responses, one thing we note is that it is not the case that operations take effect at the endpoints. That is only where the response is returned. So let's take P1. P1 enqueues 5 into Q somewhere along the segment, but we don't exactly know where this takes effect. And the same is true for P2, the enqueuing of 10. So what do you think should happen here? So perhaps let me mark. Let's say P2's enqueue takes place here, and then P1, let me place it after it. So what should happen now? What should this dequeue return?
Uh, 10.
Exactly, because that's the first enqueuing that took effect was the enqueuing of the 10, and then the second one should be 5. But this doesn't need to be the case. I mean, I arbitrarily placed these locations as the instance in time where they take effect, but that doesn't need to be the case. If this took effect a little earlier and this took effect a little later, then you would have the opposite case where the first thing that would be dequeued would then be 5, And then the next thing will be, 10. So even with a minor change, things can get interesting. We suddenly have 2 scenarios instead of just the one which we had without any overlaps. Let us think about what we just did. By making different assumptions about the point in time at which the enqueuing took effect, we have, for each case, determined a sequence of operations that would give us that exact result if we had an atomic implementation of a queue. Let's take the first one. We assumed NQ5 took effect here and NQ10 here. Then if Q were an atomic queue, this sequence of operations on the atomic queue would give us the exact same output. And same with the second case, assuming NQ10 takes effect here and 5 here, then this sequence of operations on the atomic queue would give us the same output. In other words, our understanding of the correctness of a queue has led us to defining the correctness criteria to, in some sense, behaving like an atomic queue. And it turns out this is a very astute observation. In a landmark paper published in 1990, Maurice Herlihy and Linearizability have identified a correctness condition for shared objects that they named linearizability. If satisfied by an implementation, linearizability makes the implemented object appear like an atomic object, just like the condition we have identified for the queue Q. This condition requires that each method appear to take effect instantaneously at some point within the interval of time where the method is executed. And the identification of these points was what we just did. Identifying these points are equivalent to finding a sequence of atomic operations which would justify the responses we get in some execution. And in the future, we will refer to these points as, we will refer to this process of identification of such points as linearizations. Note that linearizability is a very strong property because we cannot tell a linearizable implementation and atomic implementation to be apart. Linearizable must, by its nature, act like atomic. So in any algorithm where you employ atomic implementations, if you were to replace the atomic implementations by linearizable ones, your algorithm would function just as good. And as you would expect, the identification of linearizability by Herlihy and Wing is a very celebrated accomplishment in the field of concurrent algorithms. And we also note that coming up with linearizable implementations is a challenging task. So ever since this was specified as a suitable correctness criterion for shared objects, the design of linearizable implementations of a wide variety of objects has been a frequent research topic for this field. So we have defined the computation model we're working with and described linearizability. I will now move on to the next section where I will discuss the technique we came up with to prove linearizability. Let's go back to the thought experiment we performed a few minutes ago, the interweaving of 2 NQ operations. We know that resulted in 2 different ways to linearize them. But linearizable algorithms are designed to handle much more complicated cases where the number of operations that happen concurrently to one another and the variety of operations that can happen concurrently can be quite significant. And as a result, the number of scenarios that could take place goes through a combinatorial explosion. There are so many ways in which linearizations might occur, even in relatively simple executions. This makes it so that there isn't really a simple general way of verifying linearizability by observation. Therefore, it's important that every linearizable algorithm be accompanied by a rigorous proof of linearizability. But for the same reason, these proofs tend to be quite long, simply as linearizability by its nature is a sophisticated concept. There are simply so many cases. So for someone reading these proofs, it is difficult to verify the correctness of these proofs. And plus, the length of these proofs and the amount of detail needed in proofs of linearizability makes them quite prone to human errors. So readers are justified in their wanting to verify the correctness of such proofs. And this brings us to a question. What would be an easy to verify proofs of linearizability? Here, one option we have would be proofs that are verified by machines. You would be able to feed such proofs into a proof assistant software and have it certify that this proof is valid. And this was the approach we took in our project. We were able to come up with a technique that enables us to write proofs of linearizability that are easy to verify simply as their correctness has been verified by machine verifiers. We will soon elaborate on our technique, but we should mention that it requires some, but very little human verification. But this doesn't at all take away from the strength of the technique, because the verification we claim is a trivial syntactic check. So before going on to explain our contribution, it is useful to talk about what type of things can be proven in a way that can be verified by machines. And this requires some terminology. First, each process in the computing system is associated with a set of possible states. And for a process, its state is composed of the values of its local variables and the value of its program counter, specifically the number of the line that it's poised to execute. And algorithms specify what the state of each process should be in at the beginning of the execution. So this entails the specifying of the starting values of each variable and where the process should begin executing its program from. And this is what we call an initial state. And the set of all the processes states, each associated with it, the set of all process states, each one associated with a different process of the system, and all the states of all the shared objects which are stored in the shared memory, that is what we call a configuration. And if a configuration is composed of initial states of processes and objects, then we refer to it as an initial configuration. The system begins from an initial configuration among a set of initial configurations and moves to new configurations by having processes execute the instructions of their programs. A step of the algorithm can be thought of as a unit of computation, which consists of a process and an instruction of its program, which takes the system from a configuration to a new configuration. And a run of the algorithm is a sequence of configurations connected by steps. Let me explain how. The system starts in an initial configuration. A process then takes a step, meaning that it executes an instruction of its program, and this takes the system to a new configuration. Then another process comes in, takes a step, leading to another new configuration. We can then see how this would chain up and lead to a sequence of configurations where we transition from one configuration to the next by the execution of a step. We then refer to this sequence of steps and configurations that come before and after as a run of the algorithm. An invariant of an algorithm is a logical statement, a logical assertion that holds true in every configuration of every run of the algorithm. And an inductive invariant is an invariant you can prove using induction. More specifically, you would show the correctness of the inductive invariant in an arbitrary initial configuration. And then assuming that it holds true in some arbitrary configuration, you would then show that it continues to hold true in a new configuration reached by the execution of an arbitrary step. And as it turns out, many proof verification systems are quite effective at handling proofs of inductive invariance. And last year, as I was working on this project, I stumbled upon a specification language named TLA+, which supports a proof system named the TLA+ Proof System, whose syntax seemed quite approachable and whose capacities seem to coincide with the type of things we aim to prove. The TLA+ Proof System is among the examples of proof systems that can mechanically verify proofs of inductive invariance of algorithms. And we will later on explain how we use this specific tool to provide a specific proof of linearizability for the problem we study. So now we are equipped with all the tools we need to describe our technique to produce machine verifiable proofs of linearizability. And the core problem we are dealing with is we are given an implementation believed to be linearizable, and we want to produce a proof that this implementation is indeed linearizable, and we want to do so machine verifiably. And with our technique, doing this involves the following. We first define a procedure called a transformation for any implementation A. There are many transformations of A, and we are going to pick one that appears particularly useful for our purposes. Let us name this A prime. A prime is an algorithm that is very closely related to A, and we will define transformations shortly. But we should point out that it is essentially identical to A plus one more variable. Then we identify an inductive invariant of A prime, say inv, that is strong enough to imply a specific invariant S, which we will also precisely define in a short time. There could be many inductive invariants of A prime, but we do need a particular invariant to hold true, either as part of this inductive invariant or have it be implied by this inductive invariant. And once we have identified the sufficiently strong inductive invariant, we can then produce a machine verifiable proof for this invariant, as we mentioned before. We can do this by using tools such as the TLA+ proof system. If we end up with a machine verified proof that inv is an inductive invariant of A prime, and therefore S is an invariant of A prime, we claim this proves A to be a linearizable implementation. And this claim is due to a theorem that we first developed as I was working on my honors thesis last year. And we will state this theorem precisely after defining the concepts necessary to comprehend it. But our technique here should be clear. And most importantly, we should note that for a human verifier, the specific transformation, the invariance, and the proof, they're all immaterial, so long as it is clear that A prime is a transformation, and that there is a machine verified proof of the fact that S is an invariant of the A prime. If the verification that A prime is a transformation of A is simple, which we will show to be the case, then every other component of the proof is machine verified. And the resulting proof of linearizability is then very easy to verify. Well, this sounds quite promising. So let us begin by defining what exactly a transformation is. And we will moderate transformations with the following observation. Let's recall the Q example and how we linearize operations. What we were in fact doing there was determining an instant where the state of the object would change and the response the invoking process receives would be determined. So in fact, this is all there is to linearization, updating the state and determining process-wise responses. So shouldn't we be able to keep track of this in some data structure that would then help us capture linearizability as an invariant that's a function of this data structure? And the answer turns out to be yes. We propose this via the set of tuples. We named this set T. And this stores all tuples that correspond to some specific linearization of the operations applied on an implemented object. So in light of our observation, these tuples have two fields, a state field representing the state of the implemented object under the specific linearization represented by that tuple, and the response field that we named res that maps processes to the responses they receive as a result of this linearization. So let us add this T as a variable to the algorithm A to establish a new algorithm A prime. Here, T acts as an auxiliary variable. This means that it's only there for record-keeping purposes and has no effect on the function of the original algorithm whatsoever. It doesn't affect any of the original computations, nor does it change in any shape the flow of any processes program. So in A prime, at any line of the algorithm, in addition to the instruction that appears at that particular line in A, we also allow T to be updated. And there are two rules for this update, depending on whether the line is a return line or a non-return line. And I will describe these two rules now. The core ideas behind them are on the slide here within a single sentence, but I will take some time to explain them to make sure that they're well understood. So the first rule is if the line is a non-return line, we allow A prime to linearize a subset of unlinearized operations. This means that we take a tuple T at the current configuration and consider the set of processes whose response fields are empty. Because if it's not empty, then it means that this operation has been linearized, so we should be leaving the tuple untouched. Then, after this filter, we specifically consider the set of such processes that are currently executing some method, because these processes could also be idle, and this could be the particular reason for which the response field is empty. So this leaves us with some set of processes that are in the process of executing unlinearized methods. And under the definition of a transformation, we allow the redefining of T for the next configuration such that the new tuples in T can be obtained by having some subset of these processes linearize these operations in some order. From the properties of the object, we can easily express what this entails. For instance, if you are linearizing a sequence of NQs for a Q object, we know that this means we are concatenating the NQ elements in this given order to the end of the state of the object. If we are linearizing a DQ operation, we know that this means we are removing the first element of the state and returning to the dequeuing process. So this was the first rule. I hope what it means is clear in general. The second rule is going to be much simpler. Here, we're concerned with when a process returns something. It could be an acknowledgement that the operation has ended, or it could be a specific value. And if we look at the tuples in T, and for each tuple, look at the response returned by the specific process, if we see that it doesn't match with what we are actually returning, then we know for a fact that whatever sequence of linearizations conjectured represented by this tuple did not happen. We know for a fact that this tuple, which represents an incorrect linearization, so we know for a fact that we can discard this tuple. This tuple represents something that didn't happen. It's bad. And for the ones that remain, as the process's operation has been linearized and the operation has come to an end, and it's being returned, we can empty the response field as the process becomes idle. So this is essentially a filtering rule where we filter out all bad tuples from the perspective of the process executing the line as it returns its returns whatever value it got as a result of the computations. So in summary, transformations have this new auxiliary variable t that keeps track of linearization possibilities, and they can be updated in two ways. One, linearizing some set of unlinearized processes, or two, by filtering at return lines. Now, having provided the definition of a transformation, we can state the theorem in clear terms, the theorem that allows us to come up with this technique that we described. We claim that for an implementation A is linearizable if and only if T is not empty, is an invariant of some transformation A prime of A. This should make some intuitive sense from how we define T. We claim that it contains tuples that represent linearization possibilities. Then, if it's ever the case that it is empty, it must be that there are no possible linearizations that correspond to what the current configuration is. Hence, the object is not linearizable. We established this theorem last year as I was working on my undergraduate thesis, so I won't elaborate on this theorem too much. But the idea behind its proof boils down to an induction on the rounds of A prime for one direction, and the identification of the linearization points of the implementation A in the other direction. And with this theorem, and recalling our technique, it should then be evident to all of us that machine verifiably proving T is not empty to be an invariant of A prime is sufficient to prove that A is linearizable, so long as we can verify A prime to be a transformation of A easily, which you'll see is the case. So we have laid out our technique. We can now move on to the algorithm that we were able to apply this technique to, specifically the Herlihy-Wing Q algorithm. Here is the pseudocode for the algorithm. It is a fairly straightforward algorithm. The only line that might appear perplexing at first sight is line 6, but that really is just a for loop in disguise. So without further ado, let me briefly run you through the algorithm, what it does. We have two shared variables, L and Q, where L is a positive integer initialized to 1, and Q is an array of infinite length initialized to be all empty. Processes, as they invoke NQ operations, will claim indices from Q to write some value into. In this sense, L then represents the foremost index in Q that has never been used by any process for this purpose. And in queuing process P, first fetches and increments L into IP. So L's value is stored in IP, and then L is set to be L plus 1 atomically. P then writes whatever it's in queuing, its argument VP, into QIP, and then returns ACK, an acknowledgement that the method is done. So it doesn't return anything interesting. A dequeuing process reads L into a local variable LP. And this is going to determine the first unused index at the time of the invocation of the dequeue. And this dequeue will look through indices 1 through LP minus 1 only to find an element to dequeue. So then if this LP is 1, you note that no NQs have been invoked yet, because the first line of an NQ would have incremented its value. Therefore, there are no indices that we are going to look through to find an element to which to dequeue. That's why at this line that comes right afterwards, if LP is 1, we simply go back and restart this procedure. Otherwise, we set JP, our loop variable, with which we are going to iterate through Q to be 1. Then, one by one, we attempt to fetch and store an empty value in, one by one, we attempt to fetch and store an empty value in QJP. And if we read a non-empty value, then we have found the element we will dequeue. And we can immediately go to line 7 and return it. Otherwise, we increment JP and repeat the step. However, if we have reached LP is JP is LP minus 1, yet the value at the most recently read XP is still empty, then we haven't found anything to dequeue in the set of indices that we have chosen to inspect. So therefore, once again, we restart the procedure. You note that this is really not an optimal algorithm, because once elements are dequeued from a component that corresponds to some index, the index, this component is never freed and used for future NQs. And Herlihy and Wing were, of course, aware of this and made note of it in the paper where this algorithm was presented. They wrote that this algorithm was one that was stated with the purpose of demonstrating a linearizable Q implementation. So as such, they argue that, of course, optimizing this algorithm is possible, yet it's simply not of interest for the purpose of that paper. And secondly, we remind that, as we mentioned in the introduction, even this simple algorithm is not easy to prove the linearizability of. It took Herlihy and Wing a good 10 pages plus a sizable appendix. So for a human reader, it would be of great interest if we could provide a proof of this that is machine verified, at least for the most part, with some maybe trivial stuff remaining, which is exactly what our technique does. And here is a transformation we picked to apply our technique with. We note that initially, there's nothing stored in the state, no operations have been linearized, no processes receive the response. So T should start out as a singleton that contains a single tuple whose state field is an empty sequence and whose response field maps all processes to empty values. And let us then specify how we define our transformation. Recall that two rules that this should respect are linearizing the subset of unlinearized operations at non-returning lines and filtering out tuples with incorrect response values at the return lines. This second thing, the latter thing, is very easy to write out. So let us simply define a function filter that does this for us. Lines 3 and 7 then trivially follow the filtering rule. At line 1, you should see that I refer to a function unlinearized NQs that determines the set of processes that are unlinearized NQing processes. This can be easily defined by setting it to be the union of P and the set of processes whose response values in T are empty and their program counter at lines 2 and 3. We should point out that if it's at line 1, it really hasn't started executing its NQing yet. It is poised to get NQing soon, but it's not part of the NQing. So if it's at lines 2 and 3, or if it's the process that's executing this, then those are what we consider to be the unlinearized NQing processes. And with this defined, we can easily observe that this follows the first rule of transformations. We redefine T by picking tuples from T and a subset of unlinearized processes for which we pick a permutation, so the order in which to linearize them, and adjust the state accordingly. So this entails here processes concatenating their values, their arguments at the end of the current state sequence in the order which we pick them to linearize. And the processes that were part of this set are linearized, so we set their responses to be acknowledgement of the termination of these operations, and otherwise we leave them unchanged. Line 6 and 7 is even easier because there we only linearize the process executing the line, which by how we define A prime is not linearized until line 6 for sure. We left T untouched at lines 4 and 5. So this is obviously a subset of unlinearized processes as well. And the state is the tail of the state sequence, so everything but the first element, and the response this process should receive is the first element of the sequence, so the head. And we leave all other processes, all other responses unchanged. So this also follows the first rule. So we define T for a bunch of lines, but we left T unchanged everywhere else. We should note that this is perfectly legal. An empty set is also a subset of unlinearized processes. So at every non-return line, we have the option not to do anything with T. It should be clear now that this is a transformation of the Herlihy-Wing Q algorithm. And this reasoning here will be the only component of the proof of linearizability we are building up that needs to be verified by a human. Before writing the proof, the final step that remains to identify is to identify an inductive invariant of this transformation that is strong enough to imply the statement T is not empty. Here is a list of invariants for the transformation. I claim that these are all in fact trivial observations, and for this reason, as well as in the interest of time, I won't be spending too much time on them. But they are all easy to obtain simply by observing the algorithm. For instance, obviously at lines 1, 4, and 5, no process is linearized yet. So the response fields being bottom should be quite obvious. And no index of Q beyond L-1 is written into, hence it must be empty. or processes write in different indices in Q here, because as they obtain this IP, they increment the value of L. So every process should obtain a distinct IP, index IP to write into. So this is what this captures. So as I said, these are all simple observations. And I claim this is also probably an inductive invariant of the transformation, but we don't have anything about T not being empty yet. If we look closely, no invariant involving T has an existential quantifier of any sort. So there's nothing that guarantees that there is some tuple in T. We could attempt fixing this issue by throwing in the invariant that T is not empty as a conjunct. But then there's the burden of proof. Do we have enough facts here for us to be inductively prove that T is not empty? The answer here is no too. If we were to just add that as a conjunct, we simply don't have enough information to be able to prove it inductively. So this leads us to think that we need one more invariant, which requires some strong observation that comes with a few clever observations. Identifying the final invariant involved a fair amount of thinking. It took us quite some time as well. Therefore, I'm not sure if I can transmit the entire intuition behind it within this presentation, especially given the time limit. But to give you an idea, it involves thinking about indices in Q that refer to currently in Q things, or in Qs that are poised to happen as it is conjectured by some tuple in T. So let A be a set of such indices, and sigma the sequence in which they are conjectured to be linearized. Let us then define predicates, specifically 3 predicates. The first one, good NQ set. This asserts that A is indeed a set of indices of current and potentially future NQs. So it is a valid thing to be conjectured. Then we define good response, which asserts that the tuple T respects this conjectured set A in its response field by having matching responses to the specific conjecture. And we finally define values match indices, which asserts that the linearization order sigma is respected by the tuple T's state. Let us then identify the notion of an inversion in sigma, which means a pair of indices in sigma that appear in a different order than the one they appear in Q. This means that they are conjectured to linearize in a different order to how they're in Q. For example, some process writing to Q's index 6 will do so before another writes to Q's index 3. This is fine if the lower index that appears further ahead in sigma points to an empty component of Q. If not, there must be an active dequeuing process whose loop is past it. Otherwise, it would have been the first dequeued thing among the two if there's no ongoing dequeue that would allow for this. So this observation allows us to define what a valid conjectured order for linearization is for the sigma we have. And we can connect all this to come up with a very strong invariant that asserts the existence of a tuple in T with certain properties, which is exactly the type of invariant we need to show that T is not empty. With this final invariance, we claim that the conjunction of all invariants that we had on the last slide, plus this invariant here, is an inductive invariant of the transformation and gives us the result we want. One important thing we should note here before moving on is that what transformation we picked, what its inductive invariant was, and how we went about proving it, this all isn't at all relevant for the purpose of the reader who is simply seeking to assure themselves of the linearizability of the algorithm. The only thing that needs to be known for them is that there is a transformation of the algorithm with some invariant, which we can machine verifiably prove implies T is not empty. And we took quite some while to describe all this, the transformation, and then the intuition behind the inductive invariance. So it must be quite a relief for such a reader that they wouldn't have to do most of this. Now, with this, all that remains is to machine verifiably prove the inductive invariant we obtained. We will start by describing TLA Plus and TLAPS, the TLA Plus proof system, in very broad strokes, and then we'll provide some information about our proof. TLA Plus is a specification language that is used for formally describing and reasoning about distributed algorithms. And in TLA Plus, algorithms are expressed as formulas in temporal logic, specifically in terms of what's called states and actions. So states are logical propositions that describe the configuration of the system by stating the current value of each variable of the system. And actions, they correspond to instructions that compose the algorithm. Each line in the code of the algorithm can be thought of as a distinct action, which is a logical proposition that describes the state after the execution of the instruction, conditioned on what the state of the state before its execution is. By convention, this is how an algorithm is written out in TLA Plus. I won't go too much into the syntax, but this here is a TLA Plus specification for an algorithm with an initial state that fulfills the statement in it, So we call this an initial state predicate, and every instruction as an action that is part of the action next. And for concurrent algorithms, we can think of next as a disjunction of the line-specific actions, only one of which is executed at a time. And TLAPS is a proof system for verification of TLA plus proofs. And the TLA plus proof is a collection of claims expressed in TLA plus organized in a hierarchical format. And each claim in this hierarchy contains a statement that is either unsupported or supported by a collection of listed facts. TLAPS can certify the validity of a proof by verifying whether each claim is proven by the list of facts and definitions provided to it. So this is a big picture for TLA plus and TLAPS. And here's an illustration of what this means for our purposes. What we want to prove is that inf is an invariant of the algorithm described in spec. So in TLA plus, this theorem would be expressed as such. In every run of the algorithm specified by spec, inf always holds true. So this box is an operator in temporal logic. That means always. And as we discussed before, the proof for this would be to prove inf holds true in the initial configuration. And then assuming it holds true at an arbitrary configuration, it will continue to hold true in the next configuration. So this prime here refers to in the next configuration. So these two claims would then constitute the outermost steps of our hierarchy of claims for this theorem. And lower down in the hierarchy, for instance, if you want to prove this second statement, you would have to show it holds for a process P that executes line 1, a process P that executes line 2, so on and so forth up to 7, and then use this collection of facts and the definition of the action next to finish its proof. And then back here, these two facts and the definition of spec, which involves int and next, is sufficient to prove this claim we're interested in. This PTL is something that allows TLAPS to reason about temporal expressions, but essentially these two facts and the definition of spec are the facts that allow this proof to go through. I hope that this gives a general picture of how one goes about providing inductive invariance correct in TLAPS. So we now know what it means to prove what we want to prove in TLAPS. We want to prove that the invariant we established is indeed an invariant that implies T is not empty for the implementation A prime B described. Therefore, by implementing this algorithm in TLA+, and writing out this proof of correctness in TLAPS, we effectively produce a machine verifiable proof of linearizability. And this is what we have exactly done. So the Herlihy-Wing Q algorithm we studied, describing it only took around 140 lines in TLA+, but the proof of it spans over 3,500 lines. So this was a quite considerable effort. The invariants we listed, other than the last one, are straightforward to prove, but this is certainly not the case for the last one we listed that we named inv_s2. And to prove it correct for line 1 took more than a third of the proof. It took over 1,200 lines. And the proof is too long to explain here in detail, but it really boils down to a proof by construction for every line of the algorithm. And this is achieved by carefully picking witnesses from the tuple set T and carefully modifying them to get new tuples guaranteed to be in T in the next configuration. As I said, this proof is quite sizable. It takes around an hour and a half on my laptop when I run everything afresh for every single claim to be certified, but we end up with certified proof of the correctness of our claim. And this brings us to the conclusion of my thesis defense and my presentation. Essentially, we were able to provide a technique to come up with easily verifiable proofs of linearizability in big chunk, relying on machine verification of our proofs. And we were able to use this technique to prove the Herlihy-Wing Q algorithm, a significant algorithm that is known to be tricky to prove linearizable. And this proof has given us great confidence about the generalizability of our technique. And we are looking forward to more linearizable algorithms from the domain of concurrent algorithms. And with the insights we have gained from working on this proof, working in TLAPS extensively, we gained some insight that we hope to use to improve our proofs, perhaps by factorizing some steps to avoid repetitions, or maybe making use of the more advanced constructs of TLAPS. This was it. Thank you very much for listening. And these are my references.
Thank you, Ward. Thank you, Ward. So at this point, so there is the committee, and I see a few more students in the Zoom link. Ben, Prashant, and next to me are Siddhartha and Sucharita. If any of you have any questions or comments, please feel free to jump in and ask. Yeah, so it's your time now.
Yeah, ask away.
So I have a question. So thanks for the great talk. It was really interesting.
Thanks.
So I guess I was curious about how, could you comment about how easy or difficult it is to actually use the sort of proof assistance that you've been using? Are there any sort of IDE help? So how involved were these proofs?
I would say they're quite involved, and it really had a steep learning curve. I tried to start using it for my undergraduate thesis last year. I started working with it in January, or yeah, sometime in January, I think. And I really wasn't able to get anything interesting to be proven. So I actually sought the help of Professor Mertz sometime in March or April, and then he, with his help, I was then able to get started on working on these proofs. And as I worked on more and more stuff, I gained a better understanding of how TLAPS worked. So yeah, I wouldn't say that it is easy to get started with them. The documentation is unfortunately somewhat sparse, and it is. I hope it becomes a more popular tool in the upcoming years. But there's a very active Google group. But otherwise, there is no huge community or a wide number of tutorials that you can find besides the documentation for it. But if you want to get started, feel free to reach out to me. I have become a big fan of this tool as I've worked on the project, so I would like to help others get started on using it as well.
Awesome, thanks. I guess one more question I had was that have you thought of other properties that you would be interested in proving? I know linearizability is quite an interesting thing to prove, and it seems quite challenging. But have you given thought for what other properties you could prove with this?
Something that we want to apply this proof framework to would be mutual exclusion, and specifically we were talking about recoverable mutual exclusion with Professor Janety. He was working on that type of problem a few years ago, and to our knowledge, there is really no machine verified proof of recoverable mutual exclusion for any algorithm. And recoverable mutual exclusion is mutual exclusion on problems on systems where crashes may occur. So even in the case of a crash, we want the mutual exclusion property maintained. So to our awareness, there isn't really a machine verified proof for an algorithm that is designed for this problem. So I suppose that would be an immediate next problem to consider applying this sort of methodology to.
Awesome, thanks. Great job.
Thank you.
Or one question for you. You mentioned towards the end of the talk, firstly, I really enjoyed the talk.
Thanks.
That was more of a comment, but now a question. You mentioned towards the end of the talk that one of the invariants was almost all of the lines of the TLAPS proof.
Yeah, that's right.
The reason for this that this particular invariant was so strong that it made the other invariants easy to prove, or could you say just a bit more on why this one was so time consuming / line consuming while the others were easier to prove?
So in TLA plus terms, this was an algorithm that we had to write very intricately. So each one of the lines are quite involved logical mathematical expressions. So they are difficult to break down. And that specific invariant has an existential quantifier in it. So we need a specific witness to assert those claims in the next state. So we have to, using how the algorithm is defined, very carefully construct the witness for the next configuration of the algorithm. And because the algorithm is expressed very intricately at some specific lines, it takes quite some while to establish these witnesses and that they meet all the properties we need. Whereas the other ones are they're a byproduct of how the algorithm operates. Whereas this one, that also is the case, but we need to construct a very specific witness that is that has many different components that takes quite some while to establish in the context of TLAPS and TLA plus.
I see. That makes sense. Were there multiple quantifiers? Was there like a stack of quantifiers before the existential one? Like, was it like okay. So some sort of very complex logic in order to find the object, and then you have to establish to it that it exists. I see. Okay.
Yeah. So if you think of it in terms of a polynomial higher, like a pH, like it's pretty. It can very easily get higher.
There's
pH.
a deep stack of exists for all exists.
Yeah.
Maybe another take on the same question. You said it took 1.5 hours for the laptop to verify the proof. How did you know along the route to proving it that you were on the right track? Or did you have to sort of put faith in the fact that you were thinking logically, so it would eventually lead to a proof that could be verified?
Well, this proof took quite a while. I mean, we weren't working with the correct invariants to begin with, which we didn't realize after a very long effort. I mean, everything was working fine until we went into a very specific line for a very specific invariant that didn't come up after hours and hours of putting effort into it. So there, I was somewhat disappointed. I had good faith in that. I had a lot of faith in that specific invariance, but that didn't turn out to be the case. So we reevaluated what went wrong, and then we came up with a new invariance. And for that one, I had also put in the faith. I mean, and it ended up working fine. But this process doesn't always have to be, I suppose, faith-based, because there are. I mean, TLA plus also comes with model checking capacities. So if you can restrain the size of your state space in to a reasonable size, then you can also model check inductive invariance in limited models. With this queue, that really wasn't easily doable. We actually used this for the snapshot algorithm, the simplified snapshot algorithm we did last year. For this, we really weren't able to cleverly restrain the state space in quickly enough. So we just started working on the proof itself. But ideally, using the model checking capacities of the TLA plus toolbox, you can somewhat eliminate the leap of faith that you do as you embark on a proof of correctness for an invariant.
I see. Awesome. That makes sense. Yeah. Thank you. Or that was the last question I had.
Okay. If there are no further comments or questions from the non-committee audience, thank you for attending the talk. And at this point, I mean, the committee can remain and for the questioning.
Yeah, thank you for coming and thank you for the great questions. And I think I shall stop recording now.
Yeah, you can stop recording now. Or